All right, so this is problem 5.1.85, and can't see it very well there, but I'll read it to you. So it says two pulleys, one with a radius 2 inches and one with radius 7 inches are connected by a belt. And then if the 2-inch pulley is caused to rotate at 5 revolutions per minute, we want to determine the revolutions per minute of the 7-inch pulley. And they're giving us a hint. They say that the linear speeds of the pulleys are the same, both equal the speed of the belt. Okay, so let me make this so you can actually see it. We have a 7-inch pulley here, and then, or 7-inch radius, and then a 2-inch radius. And these have, you know, a belt connected around them, kind of a thing. Okay. And what we're trying to do, or here's the information that they give us. So the 2-inch pulley rotates at 5 revolutions per minute. So that's something they tell us. And they want us to determine the revolutions per minute of the 7-inch pulley. And they give us a hint, and the hint is actually important here. So they tell us that the linear speeds are the same, which makes sense, given that they're attached to the belt. Okay. All right, so the formula that we're going to work with in this problem is this formula right here. It's our linear speed formula. V is equal to R times omega, and omega is this funny looking W that kind of is curved up here. Okay, and so V is this is our linear speed, and R is the radius of, you know, whatever it is that we're working with, and this here is omega, and this is our angular speed. Okay. And, you know, if we don't have this formula, then this problem makes no sense if we don't know to work with this formula. All right, and the first thing that we're going to do is we're going to actually convert the angular speed of the 2-inch pulley from revolutions per minute to radians per minute. And that's so that we can work with the linear speed and eventually find the revolutions per minute of the 7-inch pulley. Okay, so let's just first of all convert the angular speed of the 2-inch pulley from, I don't normally write all of this out when I just work a problem like this. Usually I'll just work the problem, but in this problem there's kind of so many conversions and things going on that I'll write it out for you. So, all right, so we have the angular speed here, and they tell us that it's rotating at 5 revolutions per minute. So we're going to take our 5 revolutions per minute, and I'm just going to take that then and multiply by 2 pi radians for every 1 revolution. Okay, so that's going to cause, and you're going to set up this proportion however you need to get the units that you want. So if I'm trying to go to radians per minute, then I need my revolution in the bottom and my radians in the top, and I can flip this, and we will see later in the problem that we're actually going to flip this so that we can convert in the other direction. Okay, so this is actually going to give me 10 pi radians per minute. Okay, all right, so now what we want to do, now that we have this in radians per minute, we want to go ahead and calculate the linear speed. All right, so our linear speed is using this formula, and I'm going to calculate the linear speed. I'm still working with this 2-inch pulley here. Okay, so we have linear speed is equal to the radius, which is our 2 inches, and times the angular speed, and that's our 10 pi radians per minute. Okay, and you know, if you're just multiplying there, so you got 2 times 10, so you've got 20 pi, and this is now inches per minute. And the radians are still there. Radians, remember, kind of a unitless type of a situation. You can either write it down or you cannot. It's helpful when we're working with this, but you know, when you look at something and you say it's 2 pi, a lot of times we leave off the word radians, but we are talking about 2 pi radians. Okay. All right, so the linear speed then for our 2-inch pulley is 20 pi inches per minute. Now, because of the hint that they gave us, remember back over here, they gave us this hint that the linear speeds are actually the same. And so we can actually use this now. This is the linear speed of the 7-inch pulley, but it's also the linear speed of the 7-inch pulley. Okay, so that's nice. So what we want to do now is actually take this and find the angular speed of the 7-inch pulley, and that angular speed is going to be in radians per minute, and then we're going to have to convert it back into revolutions per minute because that's what they were asking for. Okay, so this problem, and we are going to finish this problem, but I just want to kind of summarize so far. Now we're working with this formula, V equals RW, well, and it's not really W, it's omega. And the angular speed, the units on the angular speed are always, you know, here in radians per minute. So since it's given to us in revolutions per minute, we first of all convert, and then we find our linear speed, and that's the same for the 2-inch and the 7-inch pulley. And now we're going to go back and find the angular speed for the 7-inch pulley. So the angular speed, you know, if you just take this V equals R omega and you solve for omega, you know, you would just divide by R, right? So we have omega is V over R. Okay, so for the 7-inch, the angular speed is going to be our V, which was our 20 pi inches per minute, and we're dividing by the radius, which is 7 inches for the larger pulley. Okay, and you know, if you remember how to deal with complex fractions, when you divide here, it's the same as multiplying by the reciprocal. So this is actually 7 over 1, right? So multiplying by the reciprocal would be 1 over 7. And your inch units are going to cancel. So then you're looking at the angular speed being 20 pi, and this is radians over 7 minutes. Okay. All right. And then, you know, they gave us the angular speed in, or they're asking for it in terms of revolutions per minute and not radians per minute. So that's, then we have to convert back. So we're now going to convert to revolutions per minute again. Okay. So to convert, we're going to take this 20 pi radians over 7 minutes, and we're going to multiply again. Now I can fidget with that relationship between 2 pi radians and 1 revolution. This time I want to put the 2 pi radians in the bottom because I want the revolution in the top because I'm converting in the other direction. Okay, and so pi's will cancel, radian units will cancel, 2 goes into 2 once and into 20 10 times. And so really we're left with 10 over 7, 10 revolutions for every 7 minutes. Okay, and that would be your answer here. So that's it.